Welcome to our presentation. We are Shy Risk Team and our project for Hack 13 is Challenge 5. Our team captain is Josh, I'm Hafsa, and then we have Alessandro, Louise and Sona. Challenge 5 was given by TfL, who manage a significant amount of assets throughout London. We were tasked with visualising the risk that flooding presented to these assets geographically on a map to clearly display areas of concern. The challenge was to use filters and data visuals to gain a deeper insight into the asset data provided, as well as using data analytics to generate risk assessments and recommendations on the environmental resilience of assets. The statements presented by our users were: I want to compare my environmental risk assessment to asset locations. I want to see on a map what assets are most at risk and filter my data to show different things. And I want to be able to create new risk assessments automatically from this data and use it to inform on where to prioritise funding to protect assets.
We had to assume the points which enclose floodplain central, outer and pan London in the risk data. We assumed central London is enclosed by Notting Hill, Kensington Park, Southend, Wandsworth, Hackney Central. We made some assumptions that maintaining a tree would cost between £75 and £410 per year, and every fifth year between £225 and £1,140 depending on size. The scope of the solution includes visualising all the assets on a map and showing each risk as a coloured area. Given a time limit, we decided to limit the scope to focus on one asset type. We focused on the risks which affected the floodplain areas. These were most all likely to lead to floods affecting the trees. We determined the trees most at risk by multiplying the height by the ground spread. Our solution takes the asset and risk data from the spreadsheets and uses Python to pre-process the data before it is imported into Power BI to create the visuals. The left and bottom images show the Python code used to determine if an asset is located within the floodplain and central areas respectively. This is done by creating a polygon which defines the area and then checking if an asset is within the area. The right image shows the Python code used to convert the categorical risk scores into numerical values before calculating the total risk score over the 3 sample time points.
The main output of our challenge was the Power BI dashboard. This homepage allows for easy navigation. On the side of the general information, you can see number of risks subdivided by number of assets, and this map shows the clusters of trees along different locations and the floodplain, as this is what we decided to focus on. The risk information tab shows the risk scores in 2020, average in 2050, and average in 2080. It also shows how many of each asset we've got, so you can see which of the most assets you have, and also risk exposure and the total risk score for each metric, so you can see where the most risk is and where the most exposure is. The Assets Trees tab shows all of the different risks that are associated with trees and their location. The map on the left shows these trees and their size and the geometry that we added to try and see the different locations. You could add different polygons to this to show the different locations if you had further location data. And you can also filter to major, minor and moderate risks depending on what you would like to see. The final tab, risk versus cost, shows the main way we think TfL will be able to use this information to decide where they need to put their attention to help manage their risk and help manage their assets. In this example, we want to see the assets, so the trees that are by the river. We also want to see the assets and the trees that are in central London. And we're also going to filter to show those assets and trees that are not protected or do not benefit from flood defences. That shows these small areas, which then shows where TfL can divert their attention to manage their assets in the best way. The colour will show the risk exposure, but due to the data, all of the trees are affected by all of the risks. So in this example, the risk exposure is the same. The size of the circles show the size of the tree, so that might then be able to be added to commercial information on how we can manage sizes of trees. For example, bigger trees might cost more money to manage, so then we might divert our attention to those with the highest risk exposure and those that are the biggest. We'll be able to add different layers to this in the future to then manage how we manage the assets and manage their risk.
If given the time, the data for the assets, luminaire point and gullies would be inputted into Power BI using the same solution that we have created for the asset tree. Due to time restraints, we decided to not include these in our scope. To improve the visual and upscale the project, we would need more specificity regarding the location of risks, rather than central, pan, or outer London. We would also require more data regarding indirect risks as this data was non-existent for the 3 assets and minimal for the other 2. We could upscale this project by acquiring more data regarding risks from other weather events, like strong winds, heat waves, drought, etc. For future hacks, we could request more risk data relating to the other assets mentioned in the asset table, like tunnels, bridges, etc. This would allow us to carry out a more thorough and accurate investigation into which assets are more at risk from flooding in London.
Our response to question 1 is by using different filters, TFL can select different assets, risks, and areas across the data set. The colors and the size of the points allow us to identify which assets are most at risk and prioritize their spending on this. Our response to question 2 is considering the gaps in the data, there was no information regarding the monetary value of the available assets that would be useful to decide whether to mitigate or accept the risk related to each asset. We would have also collected more specific data regarding risk locations and the impact of indirect risks. Quantitative rating rather than qualitative for the assets would improve the risk assessment. In addition, if we would have two variables, first for the size of the risk and second for the vulnerability of the assets, it would result in better decision making. The more risky the asset is, the greater its size, and the more vulnerable it could be. More alarming by assigning traffic light colors. We can focus on higher risk and vulnerable points. And our response for question 3 is assuming the risk is not climate related, for example, political or economic issues, we would not use geographical mapping and consider a more logical alternative. However, for climate related risk, we would reconsider the assets that we are analyzing.
Thank you for listening and for all the support provided at Project Hack 13. We really enjoyed our time at the event.